Alright, so we were discussing how to find the volume of an object that you get after rotating a curve around x-axis or y-axis, right? Okay, now in this video we are going to discuss what if we have a region that is bounded by two curves, and also we are going to rotate it around a certain axis. In that case, how are we going to find the volume? That's what we are going to learn in this video. Okay, so we have a function in this example, y is equal to 2 over x, and that's this green color curve. And then we have the line y is equal to 3 minus x. That's this blue color curve, okay? Blue color line. So now you can see there's a region trapped between these two curves, and we all know how to find the area between these two curves, right? We learned that in a previous video. Now, how about if we rotate this area around the x-axis? Now then that will create an object. So we want to find the volume of that object. How do we find the volume of that object? That's what you're going to learn. Now to visualize this, so it's the same problem. Now I'm going to rotate this region. Okay, so to convince you that in fact we get a three-dimensional object. Okay, 3D object. You can see that area, that region is what's rotating. Okay, it's making bunch of copies of that region, and you can see we get an object like this. All right, so we can take different views of the object. Okay, so that's what we get if we rotate this region, right? So how do we find the volume in this case? Now this problem is equivalent to a simple geometric problem that we learn in high school. Imagine that you have a big 3D object like a cylinder, for instance, and then you make a hole in this cylinder. Okay, now you want to find the volume of what's remaining. How do you do? How do you find this? Well, you find the volume of the larger object. So let's call V1, like the object without the hole. And then you find the volume of the hole, and then you subtract, right? What's remaining is the volume of the remaining part of this object. We kind of use the same idea. Okay, so now we still use discs, but we are gonna have a disc with a hole. That's the thing. Okay, right? So now it's going to be cylindrical discs with a hole. Now when you have cylindrical discs with a hole, the thing is that we have now two radius of the outer part, so outer radius or the longer radius, and then the radius of the inner part, so the inner radius. Okay, so to find the volume of this remaining disk, what you do is it's pi radius outer square h minus pi radius inner square h. This formula will give you the volume of the disk with the hole. Okay, so we are going to use these disks with the hole in this volume, in this object, to find the volume. Okay, right? So then if we rewrite this, so h is going to be delta x because we are rotating around x-axis, so we partition the x-axis. Okay, so then the integral formula is going to be, you're integrating between x limits, so x1 x2, you're integrating with respect to x. Now we have to figure out what's the outer radius, what's the inner radius. So if you look at the object, okay, so you're rotating from the x-axis, right? That's where you start. Okay, you're starting from, you're rotating around the x-axis. That is the center of the disk. Okay, so that's the center of this disk, x-axis. So what's the outer radius, the larger radius? Well, you connect the x-axis to the function. That's the function that's on top, that's the outer radius. Okay, and the function that's on bottom, so if you connect to the low function on the bottom, that's the inner radius. And you can see now what you are actually rotating is the stuff that's in this region. Okay, so it's the outer function, outer radius is actually the function that's on top. The inner radius is actually the function on the bottom. Okay, so it's going to be pi, okay, the function fx square, that's the function on out, minus pi, the function that's on bottom square. Okay, so then I can take pi out, so it's actually x1 x2 fx square minus gx square dx. This is the formula that will find the volume of a curve, volume of a region that's trapped between a curve, and you rotate it around x-axis. Okay, so it's the same old formula, pi and x limits, but now instead of one function squared, you have the difference of the function squared. But what's coming first is the function that's on top if you're rotating around x-axis, because it has the larger outer radius. The function on the bottom will have the lower radius, or the inner radius that's related to the inner radius. So if we set up the integral, for this problem, it's going to be, let's see. So the x values, we have to figure out where the x values are going from where to where. So we'll delete bunch of stuff. So this is 3 minus x. So the x values you can see going from 0. So we have to make these two functions equal, right? So it's not going from 0 to anywhere. We have to start the starting point. We have to find the starting points, intersection points. Okay, so we have to make these two functions equal. X minus 3 equal to 2 over x. That's how you find the intersection points. So take x to the right. So x square minus 3x equal to 2. So x square minus 3x minus 2 equal to 0. So this is x minus 2, x minus 1 equal to 0. So x is equal to 1 and x is equal to 2. So here starts at 1, ends at 2. So those are the x limits. Okay, so those are the x limits. So x values are going from 1 to 2. Pi, and the function on top is 2 over x. So it's 2, function on top is 3 minus x. Function of top is 3 minus x, because that's the line. So that's the line. So that's 3 minus x square minus function on the bottom is 2 over x. So it's 2 over x square dx. All right. So let me write that again. So the integral is pi, x values are going from 1 to 2. Function on the top is the line. So 3 minus x square. Function on the bottom is the curve 2 over x square dx. So this is the integral that will give you the volume of the 3D object that you get by rotating this region that's trapped between these two curves, rotating it around the x-axis. Okay, right. So now similarly, so if you are rotating something around y-axis, the formula changes as this. So now you are going between y limits. So it's the function written in terms of y, and the function written in terms of function g written in terms of y, and you're integrating with respect to y. Okay, if you're rotating something around the y-axis. Now here fy is not the function on top. Okay, so if you're rotating something around y-axis, then from y-axis you have to draw radius, and then you have to see which one is the larger radius. Now when you're rotating something around y-axis, the discs are horizontal, remember? So the radius going to be horizontal. So which radius is largest? So usually the radius to the right is the one that's larger. So the function to the right is what's come first. So this is the function on the right, this is the function on the left. If you're rotating it around y-axis, if you're rotating it around x-axis, first function is the function on top, second function is the function on bottom. Top function will have the larger radius. So my recommendation is, when you're rotating a curve around, when you're rotating a region that's trapped between a curve around a certain axis, draw a couple of lines meeting those functions from the rotating axis. Okay, so if you're rotating around x-axis, so likewise, like here, if you're rotating around x-axis, so from x-axis draw a couple of lines until you meet both functions. See which line is largest. That's the outer radius. That's what comes first. That's fx square. Okay, that's fx square. Function on the top, the larger radius. And the smaller radius, that's the function that you have after the subtraction, second function. And if you're rotating around y-axis, now from the y-axis, draw two lines. Okay, so that's the idea. So if you draw two lines from the y-axis until you meet both functions, see which function has the larger radius, larger line. So it's the function on the right in this case. So if we set up the integral here, well, if you're rotating it around y-axis, so you need the y limits. Bottom y value is 0, so you need the top y value. So you can find first the x value. So intersection x point is x square is equal to 2x, x square minus 2x equal to 0. So if you factor x, this is x times x minus 2 equal to 0. So x is equal to 0 or 2. So intersection points are 0 and 2 for x, but what we need is y. So when x is equal to 2, what's y? Well, 2 times 2 is 4. So the y value is 4. That's how you can find the y intersection point easily, okay? So you are integrating from 0 to 4 pi. Now when you draw the radius, what's the largest radius is the function on the right, which is x square. But you can't have x square here because you are rotating around y-axis. Remember, in the previous video we learned this. So when you're rotating around y-axis, the function should be written in terms of y. So the function here is yx square. So then the function, if you take the square root both sides, x is equal to square root y. That's the function on the right. Okay, y is equal to x square, x is equal to square root y. So it's square root y square minus function on the left, y is equal to 2x. So then x is equal to y over 2. That's what you use, y over 2 square. That's the volume, okay, that you get if you rotate this region around the y-axis. Okay, so several key important things. No matter whether you're rotating it around x-axis or y-axis, if you're rotating a region in between two curves, you need to remember you subtract two functions, squares of two functions. Okay, but you decide the order by drawing radius, drawing two lines until you meet those functions from the axis that you're rotating. Okay, and then you take the larger one, larger radius, that's the function that comes first. That's the function that you square first minus the square of the next function. So choosing the radius, that's important. Okay, now, and also if you're rotating around y-axis, you need extra work because you need to change all functions into y. Okay, you need to make x subject. Usually functions are given like y subject, right? Look at this, y is equal to 2 over x, y is equal to 2x, y is equal to x square. Now this is great if you are rotating around x-axis, you can use it as it is. But if you're rotating around y-axis, you need to move stuff around in the function and make x subject and write the function in terms of y, just like I did here. I wrote y equal to x square as x is equal to square root y. I wrote y is equal to 2x as x is equal to y over 2, and that's what I use to write the volume when you rotate around the y-axis. Okay, right, so in the next video I'll do a couple more examples, and then we can shift into another tricky lesson but same topics.